So here's a question that was sent in today. We want to express the square root of I and the cubed root of I as surds in the form of a plus bi. Alright, so first off, a surd is simply an irrational representation of a number. And what I mean by that is basically it's just left in radical form. For example, the square root of 2 is a surd, although the value of this is an irrational number. So let's consider a complex number z, and let's let it equal the square root of I. And let's also let this variable z be of the form a plus bi. So if I were to take z squared, I would get I, because square root of I times square root of I is I. And this would give me a plus bi times a plus bi. And if I were to multiply this out, I would get a squared plus 2abi and then minus b squared. And the reason why I have negative b squared right here is because bi times bi is equal to b squared I squared, where I squared is equal to negative 1, because I is square root of negative 1 times square root of negative 1, which is just negative 1. So we can say that this is equal to I. So now what I'm going to do is I'm going to rearrange this expression right here in terms of its real and complex components. So I'm going to break it up into a squared minus b squared. I'm going to put those together, and then I will put the imaginary part over here. And once again, we said that this was equal to I. So since this is equal to I, we can say that this part, the real part, has to equal 0 because there's no real part on this side of the equation. And this part right here has to equal 1 because 1 is the coefficient in front of this I on the right side of the equation. So we get two equations from this. We get a squared minus b squared is equal to 0. Therefore, a squared is equal to b squared. And therefore, plus and minus a is equal to plus and minus b. And then from the other equation, we get 2ab is equal to 1. So a times b has to equal 1/2. So in the case that positive a is equal to positive b, then we can substitute this in for this equation, and we get b squared is equal to 1/2, which makes b equal to 1 over the square root of 2, and therefore a is also equal to the 1 over square root of 2 since we assume this. So that means we can write the square root of I as equal to a plus bi, the form that we originally assumed. And in this case, a is going to be equal to 1 over root 2, and b is also going to be equal to 1 over root 2. So we can express the square root of I like this. But there's also other forms that we can express it as, because this was only one case. Let's also consider the case where a is equal to negative b. So when we substitute it in for our second equation right here, we get negative b squared is equal to 1/2. Therefore, b is equal to I times 1 over the square root of 2. And that makes a equal to negative I 1 over root 2. So when we put this in the form of a plus bi, what we get is negative I 1 over root 2 for a, plus b, which is I 1 over root 2, and then times I, so that becomes an I squared, which makes this expression simplify to negative 1 over root 2 minus 1 over root 2i. So here is the other form that we can express the square root of I in terms of. So there's another way to think about this problem that may be a little bit easier, and that is to use the polar representation of the square root of I. So for a quick review, let's draw the complex plane. We have the real axis and we have an imaginary axis. And we know from Euler's formula that e to the I theta for some theta is equal to cosine theta plus I sine theta. So if we multiply through this by r, a constant, then we get this. So I can take any point in the complex plane, like this point, and I can write it in terms of its polar form, where the distance from the origin is r, and the angle from the real axis is theta. And as theta increases, what happens is this point just travels in a circle. And once it goes 2 pi radians, it comes back to where it starts. So this polar form right here just represents a rotation in the complex plane. So let me draw another pair of axes. So here's another complex plane. We got the real and imaginary axis. But now let's consider the point I. So I would be right here, this point right here, and we know that I has an r equal to 1 since it is 1 unit in the imaginary axis, and it has a theta equal to pi over 2 because it is perpendicular to the real axis. So I can write the polar representation of I as 1 times e to the I pi over 2. And I can verify this by plugging it into this equation. Cosine of pi over 2 plus I sine of pi over 2. Well, this cancels out to 0 because cosine is 0 at pi over 2. And this cancels out to 1, which is equal to I. But we also got to remember that if this rotates 2 pi, it comes back to I. So the actual polar representation is e to the I times pi over 2 plus 2 in pi. So what this is saying is that if we go 2 pi, any multiple of 2 pi, we still come back to I. So I is equal to this. And now what I'm going to do is I'm just going to take the square root of I by taking the square root of its polar form. And this comes out to be e to the I times pi over 2 plus 2 in pi. All of that to the 1/2 power, taking the square root. So this power distributes through multiplication across these powers. And what I'm left with is e to the I times pi over 4 plus n pi. So in this case, our r is equal to 1, and our theta is equal to pi over 4 plus n pi for any integer n. So n can equal 0, 1, 2, and so on. So now if I come back up to this plot, a radius of 1 unit in the direction of pi over 4 brings me right here. And then if I add multiples of pi, this just bounces me around from this point and this point. And we can see that these 2 points, since this is 45 degrees, we can see that these 2 points are 1 over root 2 plus 1 over root 2i. And down here, negative 1 over root 2 minus 1 over root 2i, which is exactly what we got using algebra. So I can use the previous methods to evaluate this. So I can have a complex number z and let it equal to the cubed root of I, and we want it of the form a plus bi. So when I cube z, I get I, and this is going to equal a plus bi times a plus bi times a plus bi. And I can multiply this all out and set it equal to the real and imaginary components of I. And I could use algebra to get my answer just like we did before, but that is a lot harder, and multiplying this out would be a mess. So instead, what I'm going to do is I'm going to make use of what we just learned with the polar form. So let's draw our axes. We got the real and imaginary. And from before, we said that I is equal to e to the I times pi over 2 plus 2 n pi. So now instead of taking the square root, I'm going to take the cubed root. So I'm going to throw all this inside these brackets, and I'm going to raise it to an exponent of 1/3 for the cubed root. And when I distribute this 1/3, I get e to the I times pi over 6 plus 2 pi over 3 n. So we've got a radius of 1, and we've got a theta equal to pi over 6 plus 2 pi over 3 times n, for n equals 1, 2, 3, and so on. So for n equals 0, I come out a distance of 1 and at an angle of pi over 6 or 30 degrees, and I come out right here. So this is 30 degrees. And now I can evaluate theta for n equals 1. So when n equals 1, I just add 2 pi over 3 or 120 degrees from where I am. So this rotates 120 degrees to right here. And now where I am, I'm still a distance of 1 from the origin, but now where I am is I'm 30 degrees from this horizontal right here. And then if I plug in n equals to 2, I go yet another 120 degrees, and where I go is right here. And if I continue raising n, what we'll see is that we just bounce between these 3 points. So this suggests that there are 3 roots to the cubed root of I. And using your knowledge from geometry and the unit circle, we can find these points. So this point right here, which I will call 1, is just root 3 over 2 plus 1/2 I. It goes root 3 over 2 over in the real axis and 1/2 I in the imaginary axis. And this point right here, which I will call 2, so that was 1, 2 is going to be negative root 3 over 2 plus 1/2 I. And then we've got our last point, point 3, which is just negative 1 in the imaginary axis, so this can be written as 0 minus I. So anyway, these would be your answers, and they are written as a surd because they have the radicals in them, and they are of the form a+bi. So anyway, good question, and thanks for watching. I'll see you guys later.